Okay, now we continue. Hence, for each double triangle in G, at least one of its triangle is even. Okay. For sufficiency, suppose G satisfies the specified conditions. We may assume that G is connected, otherwise we apply construction to each component. There is a long sufficiency proof here, which is written in detail, but we won't talk about that detail anymore. I will talk about a little bit Beinicke's theorem. A simple, which is very important in fact. A simple graph G is a line graph of some simple graph if only if G does not have any of the 9 graphs here below as an induced subgraph. The proof is built on top of theorem of Van Roy and Wiff theorem. It suffices to show that the 8 graphs listed other than K13 claw are the vertex minimal claw-free graphs containing the double triangle with both triangles and odd. Each such graph has a double triangle and 1 or 2 additional vertices that make the triangles odd by having 1 or 3 neighbors in the triangles. The details of showing that this is the full list are not demonstrated in this presentation. The characterization in Van Roy and Wiff's theorems in Beinicke's theorem yield algorithm to test whether G is a line graph that run in time polynomial in N of G. In fact, there is such an algorithm that runs in linear time and produces graph H such that G is equal to L of H, then G is a line graph. This graph H is unique if G has no component that is a triangle. Example questions. For example, the question is, for each graph G, compute chi prime and draw L of G here. Each edge transformed into vertex here and here also. For the first graph, we have chi prime 4, 0, 1, 2, 3, and for the second graph, we have chi prime 3, 0, 1, 2. And the last example question. Use Tutt's one-factor theorem to prove that every connected line graph of even order has a perfect matching. Conclude from this that the edges of a simple connected graph of even size can be partitioned into paths of length 2. Every connected claw-free graph has a perfect matching is given. So our answer is every connected line of even order has a perfect matching. And note that a graph without isolated vertices has the same number of components as its line graph. Let S prime be the set of edges in G corresponding to a set S in V of L of G. Deleting S from L of G corresponds to deleting S prime from G, but each edge deletion increases the number of components by at most 1. Thus, G minus S prime and LG minus S have the at most 1 plus S components of any sort, odd or otherwise. For a graph of even order of LG minus S is smaller than 1 plus S implies Tut's condition. Number of odd components of LG minus S is smaller than S since the order is even. The edges of a connected simple graph of even size can be partitioned into paths of length 2. The paired vertices of a perfect matching L of G correspond in G to paired edges performing paths of length 2. Since the matching saturates V of L of G, the corresponding paths partition E of G. That's all. Thank you.